Now that we've talked about sequences, let's move on to talking about series. So what is a series? A series is simply the sum of a sequence, right? So here we have what we have written out is a series, right? It's a sub 1 plus a sub 2 plus a sub 3. So what I often find helpful is just kind of write this out for students. A sequence is simply a collection of numbers or a list of numbers in an order. The series is when you add up the terms of that sequence. And the sum would be the value, or what we would get when we add up all those terms in that series. Now, when we are dealing with series, it is often more efficient to work with something called summation notation or also sigma notation. It's also known as sigma notation because this letter that we're looking at here, this is known as the letter sigma in the Greek alphabet. But there's a couple things going on, so let's actually break it down. So first off, we're saying this right here is called the index of summation. I is the index of summation. It is simply letting us know where to start in our series. What order number are we going to start at? Where to start, right? It's kind of where we're starting. So when I is equal to 1, we're saying we're starting with the first term in our series. This is what's known as our upper limit of summation. That effectively lets us know where we're ending. So when n is equal to, let's say 10 here, we're saying we're going to start adding from the first term all the way up until the 10th term in our series. When n is equal to infinity, that tells us we have an infinite series. More on that in a little bit. Finally, this part right over here, a sub I, that's again, just like our a sub n, that's kind of like our function. It's what's defining the terms in our series. You can look at our previous lesson where we talked more about a sub n, but it's giving us a sense of how we're generating the terms in our series here. So what summation notation does is it allows us like a very efficient way of expressing what's going on with our series, right? So if we're looking at this first example here, and I asked you, let's say, let me just keep this here. If I asked you to find the sum, let's just kind of translate what's being said here in this summation notation into English so we can understand it a little bit better. We're saying we're going to go ahead, we're going to add up, starting with the second term in our series, all the way up until our fifth term, the fifth term, we're going to add the second all the way up into the fifth term of our series that is generated by this rule. So we would say the following. What does this series look like? This series that's written currently in summation notation, let me just actually remove this for a second. It's currently written in summation notation, but if I were to expand it out and just write out the series, what do we have? Well, we're going to start with the second term in our series, so a sub 2. So a sub 2 is the following. A sub 2 is negative 2 raised to the second power plus negative 2 raised to the third power. This is a sub 3. And I'm just going to keep doing this. Negative 2 raised to the fourth. And how do I know when to stop? Well, I stop at my upper limit of summation, which is negative 2 raised to the fifth power. So here is my series. I can clean up the series a little bit because it's going to make my life a bit easier when I want to add all this up, right? But here is my series. Now, what is my sum? Go ahead and add up all those terms, and I get negative 20. There's my sum. Okay? Let's try another one now. Let's go ahead and try finding the fourth partial sum and then also the sum of the series. So the fourth partial sum is just another way of saying the sum of the first four terms. Okay, so we're going to add up the sum of the first four terms. We'll notice that our upper index here is infinity because that means this series has an infinite number of terms. So we're going to start by just trying to find the sum of the first four. So let's write that out. So what do the first four terms of this series look like? Well, when I is equal to 1, right? And so probably should write this using n actually, since I use n in my general rule. So when n is equal to 1, this would be 6 over 10 to the 1. When n is equal to 2, this is 6 over 10 squared, 6 over 10 cubed, and so on. So this is an infinite series, so this is going to go on infinitely. But I'm concerned right now with just finding the sum of the first four terms. So This could be written as, again, 6 over 10 plus 6 over 100, 6 over 1,000 plus 6 over 10,000. Now, you could go ahead and try to add these all up so that they have the same denominator, and that wouldn't actually be too bad to do, right? This would just come out to the following. But something that I want to kind of highlight here, let me just actually remove that just for a second. If I were to actually write this, each of these ratios or each of these fractions in decimal form, what would that look like? Well, 6 over 10 is just 0.6 or 6 tenths. 6 over 100 is 6 hundredths. This would be 6 thousandths and 6 10,000ths. If I add all those up really easily, you could see that it would just give me the following sum, which is equal to, again, this value here. Now, why am I going through the trouble of doing that and writing it out that way? Because the second part of this problem has us finding the sum of the entire series, which is infinite. And paradoxically, that should be a little challenging for you to think about, right? Because we're talking about a series where we are going to be adding an infinite number of terms. We are constantly adding. Yet, by looking at what we've written out here, we can see that as this goes on, what is the entire sum of this series? The sum of this series is just going to be 0.6 repeating. And what does that equal to? Exactly 2/3. And that's such a cool idea in math, the idea that we can have an infinite series be equal to a finite distinct value. And that's something that you'll explore a lot more in calculus, but just kind of giving you a taste for now. I encourage you to pause right now and try numbers 1 and 2. This time we're given the series and we have to come up with the general rule so that we can write these series in sigma notation. So go ahead and pause. I will work through them in a second, but go ahead and pause and see if you can come up with it. Well, if you're back, hopefully you've had a chance to work through these. So let's think about it. Again, something that I find helpful is to write the n terms or the order terms directly underneath. So that way you can kind of ask yourself again, what am I doing to n to get a sub n? And writing it out that way, you'll see that we're doing two different things, one to the numerator, one to the denominator. What's going on in the numerator? Well, at first, those numerator values don't seem to really have a relationship to one another, but if you really think back, all the way back to our previous lesson, they're just factorials. So this is just, the numerator is simply going to be n factorial, right? So 6 is equal to 3 factorial, 4 factorial is equal to 24, and so on. They're just the factorials of those n values. What about the denominators? They are simply the exponents, or we would say 2 to the n powers, okay? So there really isn't like a step-by-step kind of process that you have to memorize here. You really just have to think and use your number sense to figure out what are we doing to our n to get our a sub n rules, okay? For our next one right over here, we see that we have an alternating series, and something that might have been helpful is to actually have you see that this is -1/2 raised to the 0. This is -1/2 to the 1. This was -1/2 raised to the second power, and so on. So writing it out that way allows you to write this as the following. We could say, if I were to start at n is equal to 0, this is simply just -1/2 raised to that n power. And when do we stop? Well, when we're raising 2 to the 7th power. So our upper index there would be 7. If you wanted to start out with your lower index being n is equal to 1, that's totally fine. That just means you have to shift that to 8. And it also means you have to rewrite your a sub n rule as n minus 1. Okay? So this is our first kind of dive into looking at series and working with summation notation. And we'll do a ton more with this, but hopefully that gets you a little bit more comfortable working with summation or sigma notation.